All right, so I saw some chat messages on the to talk about the building teams, forming groups. I encourage you to do that. Also, you can go to our forum, discussion forum on Blackboard, introduce yourself and try to find team members there. I hope that everyone can join a team, form a team by the end of this week. If you still cannot find a team to join, to form by next Monday, I want you to email me. Well, not email, but mail me in the send me a message using the mail function in Blackboard by next Monday if you still have trouble joining a team. So I can do some, grouping, pairing at that time. Also, please purchase the lab development kit. You can buy the whole kit, which is recommended, or if you already have a bunch of those components, you can certainly buy the individual parts as needed. But I expect that you'll have a development kit in hand by early next week. All right, so let me continue today's lecture. So we talked about deterministic models and abstraction layers. But when we combine these deterministic models in building a cyber-physical system, things get complex. The system is now kind of non-deterministic, mainly because the timing. Timing is not part of the software and the network semantics. So when you write your software, no matter what processors you design for, you are concerned about the correctness of the program. So the logics, the flows, how you implement the algorithm is the only goal when you write the program. Either using high-level languages or low-level languages. The correct execution of a program is what is the concern in any programming languages. In the networking domain, when you design hardware and networking software, the correct delivery of network message in all the general purpose networks that's the only concern for networking, network fabric. So you don't really write about the timing or concern about timing when you do your software design or when you send a network, send a message over the network. As a result, things that when you don't concern about time, the program will produce expected deterministic result. But when timing comes into play, for example, when you have multiple threads or multiple programs running and they share variables, and when you send messages over a network, which has delays, and that gets things out of order, and your results often the time non-deterministic. So this case is very common, and you have to step outside the programming abstraction to specify timing behavior. There are many different ways, and in different applications, you may have to choose different methods. But we're going to talk more about that. You have some tools, but it's like you don't have a very clear map. You may have to start with your modeling, define these timing clearly, the dependencies, and then go down from modeling to the design phase. But timing is really important in this cyber-physical system design, optimization. You have to be very careful and being conscious about this. CPS applications operate in an intrinsically non-deterministic world because a lot of things happen at the same time. In a factory, you have sensors, you have actuators, you have events that will happen out of order or unexpected. Your embedded system should respond to such events. And this is, the world. It's intrinsically non-deterministic. So if that's the case, does it really make sense to insist on deterministic models still? That's a good question. We say that the value of the models are still significant. In science, of course, the value of a model lies how well its behavior matches that of the physical system. For those Newton cradles, how those balls strike each other, they follow Newton's third motion law. The mathematical equation tries to capture that. In engineering, the value of the physical system lies in how its behavior matches to that model. So it's kind of the other way around. You want to build such a cyber physical system, and we start with a model, even though the model is not 100% equivalent or matches the physical system. But that's where we're heading to. The difference or the distinctions between the physical system and the model, and between the model and the physical system, is called model fidelity. Model fidelity is a two-way street. We should start with some model, even though the model is imperfect, even though the model is not 100% equivalent to the physical system. But the fidelity should be sufficient enough so that we will not divert from the physical system too far. So for the model to be useful, it's necessary but not sufficient to be able to construct a faithful physical realization. Again, we want to emphasize here, even though the models are not 100% perfect, we still want a model to serve as a starting point, and we rely on the model fidelity to give us close or as close as possible approximation to the physical system. So as we said earlier, model is represented with some mathematical equations or diagrams that will describe the physical processes or the things we want to control, we want to manipulate. The physical realization is our target. So we want to start from the model, build such a cyber physical system using computational platforms, using network fabric to implement such a physical processes. That's our goal. So the model fidelity, the way we understand, we want to use this concept is that, to a scientist, the model is flawed because, to precisely capture the physical world, you have to make a lot of assumptions. You have to assume the air has no friction, and the wires are perfectly balanced. And you have to make a lot of assumptions to make the model work or to provide this abstraction. So the model is oftentimes flawed because it's not 100% that reflects the physical processes. But that's the, what scientists perform experiments and advance the understanding of the world. They want to use models, even though this model comes from the physical processes, and it's not 100% perfect. To us, what we assume is the model is perfect. Because we start with the model, we would like to build such a model, try to capture the fundamental or the most important requirements of the cyber-physical system, the boundary conditions, the fail-safe measures, the performance metrics. So that's what we start with. And from there, we go towards the realization by building this hardware and software artifacts. So we follow this path from the model to the design. So the realization is actually flawed because we're building this working prototype, try to meet the requirements or meet the specification of the model. So that's what we want to make on this model fidelity. So for CPS, the question is not whether deterministic model can describe the behavior of the CPS with high fidelity. We don't have to argue about deterministic or non-deterministic, whether one way or another. The question is really whether we can build a cyber-physical system whose behavior matches that of a deterministic model with high probability. So that's our goal. Again, we start with a model, which in most cases it's designed, captured as a deterministic model. Given the input, given the state, we know exactly the next state is going to be. And from this given model, we will design our cyber-physical system. Or in other words, we're going to build this embedded system with computation, with networking, with sensors, and with actuators, so that this system has the behavior that matches the model we start with. And we want to match that with high probability. Because things may go wrong. There are cases that you didn't expect or envision at the beginning, and the component itself may malfunction. So there could be a non-deterministic thing happen after you build this system. Deterministic model do not eliminate the need for robust fault-tolerant designs. That's what we also gonna consider, resilience, adaptability. In fact, all these things will enable such designs because they make it much clearer what it means to have a fault. So the model, as a start, you want to consider all these different situations, boundary situations, as much as possible. This will save you a lot of time and effort down the road when you suddenly find out, oh, your design just missed one important possibility that this piece may go wrong, or the packet may be dropped, and then your system should, by design, accommodate or cope with such situations. So we have to fix the models, to start with some models. And this course, especially the next couple of lectures, we're going to look at the models. So next week, we're going to talk about the state machines, as the discrete dynamics. When we talk about quite a few examples how we capture these requirements using models.